Hello, and welcome back to Introduction to Astronomy. So, our first segment, we're going to talk about the ideal gas law. Because, after all, stars are basically big balls of gas. So, we can describe how those gas molecules inside of that star are behaving by using this formula. And so, it's going to, a particular gas is going to have a pressure P. Okay, and then it's going to have a volume V. N is going to be the number of gas molecules. So normally a star is going to have trillions and trillions of gas molecules inside of it, so N is going to be a very big number. And then T is going to be the temperature of the gas. Okay, then it also has a fundamental constant. So you'll notice that most of the time these formulas that I talk about, they have some kind of a constant involved. And so this is the fundamental constant of nature that goes with gases. And it's going to be called the Boltzmann constant. Now we don't really care about it, so we'll be able to use this formula without referring to that letter K, but it actually is part of the formula. So I want you to have a feeling for how this formula works. Pressure times volume is going to be equal to nKT. Okay, so let's draw a picture then of a typical cloud. Okay, now this typical cloud is going to have inside of it a certain number of gas molecules. So that's going to be the N. Okay, then it's also going to have a certain volume V, and then it's also going to be under a certain amount of pressure. So the pressure inside of this gas is pushing outwards. So think about a balloon. The reason why a balloon doesn't collapse is because there's pressure inside of it pushing outwards. But for our purposes, it's sometimes better to think of the pressure as being pushing inwards on this thing in order to understand the formula. Now it turns out that the pressure on the inside is going to be equal to the pressure on the outside, otherwise the balloon would start to expand or the balloon would start to collapse. So it's easier again though to think of that pressure as being on the outside. And then this little volume of gas is going to be at a certain temperature T. So those are the things that go into this formula. And so the formula is going to say that pressure times volume is equal to N. Now we can get rid of the K and just say that it's NT. So for our intents and purposes, we're going to say that this is our formula that we're going to work with. Pressure times volume is equal to the number of gas molecules times temperature. All right, so let's do some conceptual type questions involving this thing. So imagine that you've got a balloon, and that balloon has a certain volume and is at a certain pressure. Now what you're going to do is you're going to squeeze the balloon, and we want to know what's going to happen to the pressure if you do that. Okay, so the volume used to be this big. We're going to apply pressure to it, and so it's going to make the volume get smaller. So if the volume gets smaller, what has to happen to the pressure, assuming that the temperature doesn't change? Now the N can't change. The N is the number of gas molecules that are inside of it. So if the balloon is tied off, so the N isn't going to be changing. And we're just going to say, for the sake of argument, that the temperature is not going to be changing. So that if we apply pressure and it causes the volume to go down, then what did the pressure do? And so in order to figure this out, you have to just remember that, for example, 4 is equal to 4 times 1, but 4 is also equal to 1 times 4. Now in this case, the volume is getting smaller, So let's say the 4 is going to 1. It's getting smaller. What do you notice happens to this number here? So this number is getting bigger. So as you increase the pressure, the volume decreases. And now that's only true because we said that the temperature and the N were not changing. So that would be like the 4 over here. That number is not changing. Okay, let's try another example of how to use the formula. So this time, let's say that you got this balloon and we're not going to do anything to its volume. So the volume is going to stay the same, okay? But what we're going to do is increase the temperature of the balloon. What happens to the pressure? Okay, again, it's got the same number of molecules inside of it, so the N doesn't change, the V doesn't change, but we're increasing the temperature, and we want to know what would happen to the pressure. Okay, now in order to understand this time, what we remember from algebra is whatever you do to one side of the equation, you got to do to the other. So that, let's say that I double the temperature. So if I double the temperature, I have to multiply this side of the equation by 2, which means I have to multiply this side of the equation by 2. So that the pressure would double. If I double the temperature, I double the pressure. So these are some things that I'd like for you to be able to do, just with some simple numbers. So we're not going to be plugging in, you know, like that the volume of the balloon is 1 cubic meter and the temperature is 120 Kelvin, and we need to know what's the pressure in pascals. Okay, that's what you do in a chemistry class. So what we're going to do is just kind of like simple numbers. If this number doubles, then what does this number here on the other side have to do? So here's another example. If the pressure on a gas triples, what happens to its temperature? Okay, in the previous problem, what we did was we changed the temperature and we asked what would happen to the pressure. So this time we're reversing it and we're saying if the pressure on a gas triples, what happens to its temperature? So we take our working formula, PV equals NKT, and so we're going to triple the pressure. So multiply one side of the equation by 3. So that means we multiply the other side by 3. So that means that the temperature is going to triple. Okay, so now what we're going to do is use this in order to explain the inside of the sun, and we're going to do that in the next segment. So I'll see you then.